Okay, welcome to lesson 3 lecture for multivariable. Lesson 3, we're talking a lot about perpendicularity, and we're going to talk about planes and cross products, a lot of new things that we're talking about in this lesson. So jump right in, we're going to talk about how to find a cross product of two vectors by hand. So what you want to do is you want to set up a matrix, 3 by 3 matrix, the top row being ijk, the second row being one vector, and the third row being the second vector's coefficients, and you're going to find the determinant of that matrix. I don't know how you guys learned to find determinants. Whatever way you learn is fine. This is the way I learned, and I like it, so I use it this way. So what I do is I copy down the first and second columns like so. And basically just do some multiplying. So for example, I get A2B3I plus A3B1J plus A1B2K, and then I subtract A3B2I A1B3J and A2B1K. All right, so that basically would give me, if I subtract the i's and the j's and the k's, it would give me this vector here. So A2B3 minus A3B2, and then A3B2 minus A1B3, and then A1B2 minus A1B1. As my cross product vector. Important to note here, the cross product of two vectors is perpendicular to both of those vectors, which makes the cross product very important in 3D world. So a quick example here of finding the cross product. So I'm going to set up my matrix. Find the determinant of that. So I'm going to copy down my first two columns. Okay, so my cross product is going to be 6i minus j minus 2k, and then minus 1i plus 4j plus 3k. So that gives me 5i minus 5j minus 5k. So the cross product of A and B, this is vector 5, negative 5, negative 5. One use of the cross product is to help us find the area of a parallelogram or a triangle. So we might know the area of a parallelogram as base times height, right? But we're also going to say that it's the cross product of two vectors x and y. So I'm going to draw a parallelogram here. Okay, in this parallelogram, we'll say this is vector x over here, and this is vector y over here. Okay, so the base and the height of this triangle, actually I don't want to use x and y since I already have x and y up there. Use different numbers here, so we'll call this v1 vector 1 and call this v2 vector 2 over here. base height of this triangle, obviously the base is just vector 1, so it's magnitude of vector 1. And the height of it, if we were to draw this in, we call this angle theta down here. Some simple trigonometry, right triangle trigonometry, would tell us that the height is going to be the magnitude of V2 sine theta. Okay, and that actually is going to equal the cross product of x and y. So to find a triangle, obviously we know the area of a triangle is just the area of a parallelogram. So put area of a parallelogram divided by 2. So therefore, the area of a triangle would then be 1/2 of the cross product of 2 vectors. Again, we can name the vectors anything you want. I call them x and y. You can call them v1, v2. It doesn't really matter. It just matters that the cross product between 2 vectors would give us the area of a parallelogram. Okay, unit vectors. I know you've done unit vectors before. I don't know if you've done them in 3D, but to find them in 3D, it's the same thing. You take your vector and you divide it by the magnitude of that vector. So an example here of unit vector of A. So we're going to find the magnitude of A. It's going to be root 4 plus 9 plus 1. So it'll be root 14. So the unit vector in the direction of A, I'll call it unit A, would then be 2 over root 14, 3 over root 14, negative 1 over root 14. No need to rationalize anything like that. We're good there. All right, page 3 here, we have the Xyz Equations of Planes. So the Xyz equation of a plane with normal vector ABC through any point, random point, x1, y1, z1. You see the work there. So first thing you want to do is do the dot product of 2 vectors here, the normal vector that we're given, and then a random vector xyz minus x1, y1, z1 set equal to 0. So find the dot product, simplify, simplify, simplify. Set everything with x, y, and z's to one side and all their constants to the other. And we talked about this in class briefly. This is what you want to write your equation of a plane like. This is your standard form of an equation of a plane. Feel free to pause the video and copy that down if you need some extra time. All right, so we're going to look at example 3 here. We're going to find the XYZ equation of a plane through those 3 points. Up above there, you can see I have like little instructions on how to do that. I'm going to find 2 random vectors in the plane, for the normal vector to those vectors, and then use that formula that we just came up with above. Okay, so finding 2 vectors here, there's technically, I guess you could say 6 different vectors you could use, because you could go PQ or QP, QR or RQ, PR or RP. It doesn't really matter. There are different answers to this, but it should all pretty much work out the same way. So I'm going to do vector PQ. So vector PQ is 2, 1, negative 3. And do vector PR. So vector PR is going to be 2, 3, 2. All right, so I got my 2 vectors in the plane. Now I'm going to find the normal vector to those vectors. Basically, it's saying use the cross product, because the cross product would be normal to both of those vectors. Okay, so set up my cross product here. Again, this is just how I find my cross product. You do not need to do it this way. If you prefer another method of finding the determinant of this, it's absolutely fine. So let's see, I get 2i minus 6j plus 6k minus negative 9i plus 4j plus 2k. So my cross product yields 11i minus 10j plus 4k. Or the vector 11, negative 10, 4. So we found our normal vector. Now we're going to use the formula that we have up above there. This one right here. All right, so our normal vector 11, negative 10, 4 dot product of, so pick any point here and do x, y, z minus that point. I'm going to use r. So x minus 3, y minus 6, z minus 2. Equals 0. So the dot product would be 11x minus 33, and then minus 10y plus 60, and then plus 4z minus 8 equals 0. Keep your x's, your y's, and your z's on this side. Combine like terms and add to the other side. And this is the equation of the plane that goes through those 3 points. Okay, last one is something you did, I want to say, in try 2 already. But now if we want to do this by hand, we're going to plot an ellipse on a random plane. All right, so how do we do that? We need a point on the plane to be the center, and then we need 2 perpendicular unit vectors to represent the direction vectors of the plane. Okay? So we're going to try to plot the ellipse x squared over 9 plus y squared over 4 equals 1 on that plane 2x minus y plus z equals 8. All right, the first thing we're going to do is we are going to just find a random point on that plane and be our center. Okay, so if you put 0 in for x and 0 in for y, that would give us z is 8. So we're going to let our center be 0, 0, 8. The normal vector to our plane is going to be the vector 2, negative 1, 1. It's the coefficients of x, y, and z there. All right, then it's a random point for us to be on that plane. Let's do, if we put 0 and 0 in for y and z, we would get 4 for x. So another point would be 4, 0, 0. Keep it as easy as possible here for us. Okay? All right, so the first thing we're going to do is we're going to find 2 vectors, 2 unit vectors here. So one vector, we're going to do the point minus the center, and we'll just call this vector 1. So the point minus the center is going to be 4, 0, negative 8. Now, because you can simplify this, might as well simplify this a little bit. Divide everything by 4, you get 1, 0, negative 2. Always better to use smaller numbers if possible. Same vector, just multiplied by a scalar factor of 1/4. So v1 is going to be 1, 0, negative 2. Okay, we want to find the unit vector of that in the same direction of that. So the magnitude would be root 1 plus 0 plus 4, which is root 5. So my unit v1, I'll call it unit v1, is 1 over root 5, 0, negative 2 over root 5. And we have one of our 2 unit vectors. To get the second direction vector, we're going to use, well, what you could do is you could use a unit vector and a normal vector to find a second direction vector, but it might be easier. And what I'm going to do is I'm going to use the normal here and this one, and then I'll just find a new unit vector in that direction, because I don't want to work with fractions and have radicals in it when I'm doing my determinant. All right, so ijk, and my first vector, which was 1, 0, negative 2, and my normal vector So I get 0i. Now let me finish my setup here. So I get 0i minus 4j plus 1k minus 2i plus j plus 0k. So my new vector here is going to be -2, -5, 1. So then I got to find, I'll call that V2. The magnitude of V2 is 4 plus 25 plus 1, square root of that. So that'd be root 30. So my unit V2 is -2 over root 30, -5 over root 30, and 1 over root 30. And that's pretty much it. Now we can write our vector, or ellipse equation out. So we'll call it P of t. Your center is 0, 0, 8. Look at the radii of the ellipse. The long radii is 3, the short radii is 2. So make sure you put a 3 or a 2 in front of one of these or the other. So we got 3 sine unit V1 to make that radius be 3, because we know that unit. I forgot my sine t. There, 3 sine t times the unit vector. Plus 2 cosine t times the other unit vector. And there we have our ellipse that would be on the given plane. All right. If you have any specific questions on it, you can shoot me an email. Otherwise, that will be it for lesson 3.